Okay, so in this video clip, I'm going to explore the links between the trinomial model and the binomial. And the trinomial model is based here on Phelan Boyle's paper coming from March 1988, published in the Journal of Financial and Quantitative Analysis. And so he built, or he expanded or extended the analysis provided by Cox, Ross, Rubinstein for the binomial approach to option pricing. Again, there's a few links you might take a look at here in the Google Colab. I'll leave a link to this Google Colab below the video clip. You might take a look at the VinegarHill site where I run through an explanation of the trinomial model, and I have some video clips there presented sequentially how you'd set up the trinomial model in Excel and do some basic modeling of the lattice framework. That might be, if you're new to trinomial models, that might be useful to take a look at. Go into the VinegarHill webpage. And also the video clips are provided here. So a more direct way of looking at the visualization and Excel mapping and setting up a 9-step manual trinomial tree, which I will use here in this video clip, are presented here, right? So this is something perhaps of some interest, and the Google Colab implementation. So those are all video clips, and I encourage people to take a look at if you're very new to the trinomial model and binomial model frameworks. Okay, so the motivation here is there's a paper also by Rubinstein, Mark Rubinstein, 2000, and he sets out the relationship, or tries to set out some kind of the links or explore the links between the binomial and trinomial option pricing model. And in this video, I'm going to explore a little bit the maths here and then a little bit of the logic. So really what he's saying is that if we consider the traditional binomial framework where the value of the, if we think of the stock price tree and then the option price tree, we see a series of nodes, but embedded in this binomial, perhaps we can see a trinomial type configuration. So to garner a little bit his insight, he says it was natural to ask the question of how binomial trees were related to trinomial trees produced by explicit finite differences. I had a sense that that if the world worked elegantly, a binomial tree ought to be a special case of a trinomial tree. Trinomial trees ought to be composed of binomial trees, somewhat like molecules are composed of atoms. One could hope that the trinomial tree could be parameterized so that it could be interpreted more fundamentally as a binomial tree in which every other period were simply skipped. And of course, he provides a schema for us to kind of consider that. Again, if I go back to the Colab, I found that this link to Andrew Morris's PDF file here, he explores also the binomial equivalence to the trinomial model. This might be a more intuitive way of looking at that. If we consider this as being, our typical binomial framework where we have 1 step, 2 steps, then embedded in that 2-step tree, we have many of the outputs of the trinomial. And if we were to try and explore a little bit the equivalence between the binomial and trinomial, in the binomial framework, typically when we consider the asset price, stock price going up and then up again, we come here, perhaps that is U from the trinomial. And if you go up U and D, the binomial tree, the Cox-Ross-Rubinstein tree recombines. So if you start off here at 100, multiply by U, then D brings you back exactly to your starting point, 100. So that's like M. In the trinomial tree, M is equal to 1, and then D is equal to the D squared of the binomial. So the capital D here for the trinomial, which is the step jump, is equivalent to the binomial D squared, and the trinomial U could be made equivalent to the U squared, and then M would be equal to U by D. And likewise, we have a similar sort of a pattern emerging here in terms of the risk neutral probabilities. Okay, now again, the purpose of this video is really to explore under what circumstances is the binomial trinomial likely to be equivalent, and then perhaps understand as well under what circumstances they're not going to be exactly the same. Okay, so if I go back then to our starting point, previously when we had run through the video clips that I had here, I'd introduced a few snippets of code for the trinomial in C++, using static memory, using dynamic memory. You might explore those in the video clips. But typically, when you're running a trinomial model, you'll have a series of parameter inputs, S, K, R, Q, V, T, C, A, and then a number of steps. So for instance, the stock S is the stock or asset price, K is the exercise, R is the risk-free rate, Q in this instance dividend yield, V is 20%, it's the volatility of the underlying annualized return, T is the maturity of the option, C denotes is it a call or a put, C is a call, A being American, E would be European, so A here denotes American. And if we run this snippet of code, execute, it will go into the content folder. So it's appeared now. So main CPP is the name of the C++ file, which we can run in Google Colab. And then to get the output, we use the bash command. And using these actual parameters that we have here, we're getting a value of 9.066. Okay, so the parameter inputs that I'm using are based on Brody to Temple 1996. And if we had set the step size to 15,000, which is a fairly big tree, we would be getting a value down here of close to true of 9.066. Okay, so we can use these as benchmarks. Now, this is for the American option. And of course, it's simple to change it to European. We could change to E, and we can change this to 9 and run. 9-step tree, if we execute that and run, and then come down here, we will get a different value, right? 721. And we can see how that compares against an actual Excel spreadsheet. So I'm going to put American A, 9 steps, run this again, and we're getting 878. So basically, when I run a C++ file in Google Colab, it posts initially, takes the script that I've written, and then it puts it into the content folder. And then we call that using a bash command to execute, and we get our output for if it's a function that we've set up. And normally in Google Colab, the native code is, or the native script is Python, but you can run C++, you can run MATLAB, you can run R. Likewise, below here, I have some R code. And if I want to execute R code, I load in the magic command to run R commands. And then whatever R code I have, this bit of code I took from Detail and Verts, and it's also based on this style of coding here from Espen Hogue, right? And I'll leave a link to that. Well, Espen, we might take a look at Espen's website for a second. Espen has a couple of textbooks. One in particular we make reference to a lot is the option pricing formulas, where he sets out a number of option pricing formulas in VBA for Excel. And his lattice structure is quite efficient. He uses dynamic memory, and we replicate that here in C++ and in R. So again, if I was to estimate a trinomial tree using R code in Google Colab, no problem. We load in this command, and then we run whatever snippet of R code. But if you have some R code, you must introduce percentage R before the R code is executed. And then we get some output here. And the value we have is the same as before. Now, if we change our option to being leave it as being American, take the step size down to 9 and run that, we get a value of 878877. So that's the same as what we had looked at from before, right? So that's the, again, if we think of the parameter inputs we have here for the trinomial model, we've A, we have C, so it's an American option, it's a call, the stock price is 100, the exercise is 100, the maturity is 3 years, the risk-free rate is 3%, the dividend, okay, B is the cost of carry, which is the same as B or negative Q, and then we have sigma 0.2 n equal to 9, right? And we can make explicit, I mean, we're going to, we'll see that in a moment, but we can also output the U, the D, the M, the PU, the PD, right? And maybe we'll do that in a moment. For the binomial model, and again, this code we took from Dietheim-Wurst. I'm going to run the binomial Cox-Ross-Rubinstein model here, and I'm going to leave you this link. You might just take a look at the source code for this binomial model. Now it's R code, not C++, and I just grabbed the CRR binomial model from here, right, and made a few small changes and introduced, and now it's live. So if we run the C++ code, again, if I come down and I say, look, it's for stock price 100, so the same values as before, but we'll change this to 18, right? And it's American. We'll run that and see what happens. We get 8988. It's not the same as for the trinomial, but if I change the trinomial to E and execute, I'm getting 721. And if I change the binomial to E, so CE would denote European call, we'll get the same result. So again, exploring the relationship between the binomial and trinomial, what we immediately observe here is that if we, and I've summarized it here in this Excel spreadsheet snippet that I've included in, but if we run, maybe I have it below yet. So this result here, if we take the trinomial model and the binomial model and put in these parameter inputs for the trinomial and for the binomial, so it's the same, and it's the same as what we have above in the R snippet and the C++. Then if the option is American, the trinomial model and the binomial model are producing different results. But if it's European, and we take those snippets, the binomial and the trinomial produce the same result. So the question then is, why in the case of the European option are we getting an equivalence between the binomial and trinomial, but not with the American? And notice that we've followed Rubinstein's. Rubinstein has pointed out, look, if we go back to the table of contents here for a moment, you know, if we skip, that is, one could hope that the trinomial tree could be parameterized so that it could be interpreted more fundamentally as a binomial tree in which every other period were simply skipped. So if we have here the binomial model and trinomial, if we double the step size and make the option European, we get the same value for the option. So that the value of the European call, whether it's trinomial, binomial, using the same parameter inputs, doubling the step size for the binomial relative to the trinomial, we're getting the same option value. That doesn't stand for the American option. Okay, so to explore that, maybe I'll go into Excel and look at some of these relationships, and let's see if I can line this up a little bit better. So we have here an American option, right? Maybe just to explore a little bit. Okay, so this is the live spreadsheet, if you like, of the trinomial relative to the binomial. And notice that if I change, and again, these functions are coming from Espen Hogue, VBA functions, but we've got the same results coming in from the C++ and R code in Google Colab. But if we change the designation of the option from being American to European, so if I change this to E, and I change this to E, notice that the values down here are the same. Now we could play around here. What if I go to 90 here and 90 here? Notice that the value's exactly the same. If I change this to 2 years and this to 2 years, the values are exactly the same. And if I change the volatility to 30% and the volatility here to 30%, we're getting exactly, so we're getting equivalence between the trinomial and the binomial model, where this is a Cox-Ross-Rubinstein binomial model, and the trinomial model is based on Phelan-Ball 1988. Okay, so let's go back to the original results that we had. I'm going to copy and just paste across here. That might be the simplest. And you notice we're getting the same result. If I change this to A and this to A, we get different results. Okay, so that's an area that we might explore. Now, if we take these results again and explore, right, come back here for a second. So this is a trinomial model, same parameter inputs. Take a look at the outputs that I'm getting for U and D. These are the trinomials, so I better be clear. It's the trinomial outputs, trinomial U, trinomial D, trinomial PU, PD, and PM, right? And I follow the formulation set out by Boyle. This is Boyle, 1988, that if we have these parameters, now this is sigma, V denotes the sigma, and the delta T is the number of years divided by the time step, right? So delta T is the number of the time period, capital T, divided by N, delta T, right? And if we estimate U and D using these formulas, these are the results that we get. And likewise here, PU, PD, PM. And we built our tree by multiplying. This is a 9-step tree, and we multiply by U, we multiply by M, right? We multiply by M, which is 1 just itself, and multiply by D, right? So M here is equal to 1. And in the trinomial model, the nodes repeat themselves as you go forward. This is the stock price tree. But then to value the option, right, we take the value of maximum S, the S we generate minus the exercise, the intrinsic, and then we pull that, we perform a backward recursion where we take the maximum of the intrinsic value or the time value of the option, the continuation value of the option. And if we want to convert this to euros, so okay, we do that. And you can see as we pull back through the tree, and I've done some more video clips here on this, we ultimately produce this value for the American option. So that 878 corresponds with the 878 here from our VBA code. So we create the stock price tree, and then we do a backward recursion, and we get the value of the American call. But I've also done that here in the Colab, where for the American option, you can see we had a value. If I change this to CA, That's the binomial. If I change this to American and run again, we get 878. So that's the same. Now, if I want to explore this a little bit further and output C, now remember in the trinomial model, we calculate U, we calculate D, PU and PD. We can output those. So that we explored those a moment ago. We can even take DT. We can say, okay, I want the value of the model. I want U to be outputted out. I want D. I want PU. Maybe I want, do I have explicitly M? Okay, U and D, M is equal to 1. PU, PD, PD, and PM, and perhaps DT. Right? I don't need DT. Okay, and close the brackets. Right, and let's run that code again. And this time I get the value of the option. So for the American option, I get U 117D is equal to 0.84 or 1 over, it's equal to 0.84 PU. So we have U, D, PU, PD, and PM, right? Okay, so let's just copy that and go back into our manual copy selection and go back into our spreadsheet for a moment and see are the values we obtained here in the manual estimation equivalent to what I had obtained in R. So let's just paste. And you can see, yes, the value for the American option is the same, 117, 0.84 for D, PU 09126, PD is the same, and PM, right? Now, interesting thing here is, let's go back for a moment into Google Colab and have a look at our values again. And what if I change the option to being European and run this trinomial tree? None of the values for PU, for U, for D, PU, PD, PM have changed, but the value of the option has changed. Again, to understand that a little bit, we can go into our spreadsheet again. We can create a copy, move our copy, and we'll come down here to trinomial American call, create a copy. So it's a straight copy. And we'll say, look, it's not going to be, in this case, American. Let's make it European. European. And return. Now, the only change that is required for an American option, we change this from A to E, we get European. And we get that 721. Let's take out this value here for a moment. That's the American option. For the European option, we don't have early exercise. So basically, we can remove this maximum element. And we just adjust that. And let's pull that down. And this is the 9-step tree. So the value we should get in the apex is the 721, right? And note what we're doing here. We're doing a backward recursion where we're using the PU, the PD, and the PM set out here, right? Okay, so let's continue that. And if we do this correctly, so just drag it across and update the formula changes and the backward recursion value changes. Now, in the actual estimation that's being performed, the series of steps I'm going through is very much the type of, it's consistent with the estimation that you would typically would be performing. So this is what's implicit in the mathematics of backward recursion. You're pulling the time value back and you're using the PU, PD, and PM as weights, right? So as we go progressively back, we're getting closer to the 721, right? And let's drag that down. And then the value here, we just pull it back. And we hit that 721, that value and that value there tally. So this is the value for the European option, and we would say this is European, right? So this is the European tree, not the American tree, it's the European. So by making that change. Now the European tree, right, and the binomial tree produce the same results. The binomial European and the trinomial, we can create equivalents if we use the American option. The problem is really with the relates to the stopping and the continuation. Okay, so we'll explore that a little bit in a second. Let's go back to this Colab for a moment. Let's take the results. Remember, in this C trinomial, we had UD, PU, PD, PM. We outputted here. Let's take these values again, copy, and go back in and see if we can link it into what's going on in the spreadsheet. Right, home, paste. And you can see, okay, the value is the same for the American option. PU, U, D, PU, PD, PM, they haven't changed. Okay, so we will still have in the American and European option, we still have the same stock price tree. So using the trinomial call option, the tree didn't change. The stock price tree is exactly the same for the European and American option. There, we didn't change anything there. It's the values here are changing, right? Okay, now let's have a look at the binomial for a moment. Let's go back into Colab and explore this just a little bit further. Okay, so we've looked at the trinomial and the binomial. They produce the same results, right? So if I take, for instance, below here, come down, use this binomial code, and we have an 18-step tree. It's a European call, stock price 100, exercise 100, time 3 years, risk-free rate 3%, cost of carry -4 sigma. So these are the same parameter values as before. And we can include in, we can do what we did before. We could say, let's take something like this, copy, come beneath here. Now in setting that out, return value. Okay. Okay, so let's Control V, and we'll just say, okay, let's take this option, copy, and replace Control V. And we can remove this. So basically, in this case, we're going to get a new U and D and P, right? We don't have a PM here. So PU, so we just have P, and PD is 1 minus PD. Okay, so we need to get P, and 1 minus P is PD, right? Is equivalent to PD. Okay, let's run that. So we have a value of 721, which is the same as for the trinomial model. And then if we look at our 1085, and we compare to what we have here, the easiest way to do this, let's just minimize and put this, bring this up. And we can compare, right, to our trinomial model here. So these are the outputs for the trinomial. These are the outputs for the binomial. Okay, let's just verify. If I take this value, and copy, so copy, okay, I'll have to write it manually, 1.08 50756 and put to the power of 2, and let's execute. Okay, or just multiply it by itself. Multiply. So this is Python, and you should be using Python script here, right? Copy, cell, and paste. Control V. So copy, selection, paste, and run. The value should be the same as what I have here, right? Demonstrating the result from if we go back to the result we had before. Basically, if we take the mathematical relationship, if we square the binomial u, we get the trinomial. If we take ud, we get m. If we take d squared, we get d. Okay, so let's compare that again. Just do one more check. So again, we're exploring the links between the trinomial and the binomial. This is the binomial. And again, if I take 0.84, copy, that's the, or I'll take the 0.92. Let's take this one, right? So 0.921.921 59048. So this value here we've put here, and we'll multiply it by itself. So I'll just copy selection and multiply by itself. Control V. We get the value here, 0.84. And again, with the PU, if we take our value here for PU, if we take PU squared, we get the trinomial. And if we take the PD squared, we get the trinomial. Let's just explore that value for a second. So if I take 0.43 from the binomial, 8.9, so this is PU, 8.98550, and multiply by itself. So take this, copy, this is PU from the binomial, Control V, paste again, then the value we should obtain is our equivalent to our PU. So 1, 2, 3, 4, 1, 2, 3, 4, this 19. And we get 192681. So you can see we've constructed, or we've been able to describe the equivalence between the trinomial model and the binomial model. And when you're estimating European option, it's very simple to replicate the trinomial result with the binomial result. We just double the number of steps, right? So for instance, if we take for a moment, if we took, let's say, put this to 110 and run this estimate, and then change this to 110, or better again, let's change it back to 100, and let's change from being a call to a put, right? We're basically going to get the same dynamic here at work. So we'll change this to PE, European put. Let's run. And what we observe is the same relationships can be observed here in terms of the estimation. The value of the put, European put, coming from the binomial and the trinomial are exactly the same, no difference. But for the American options, then we're going to get a difference. So if I change that to PA, and execute for the binomial, and execute here for the trinomial for the American option, right? We're going to get different values. Now, it didn't execute early, so if it's CA, there will be a difference. So, okay, if there's no early exercise, the American option will be equivalent to the other American option. If there's no early exercise, how do I know there's no early exercise? Well, if the value of the American option doesn't exceed the European. So if I change back to E here and run, the American call, so it should be a call here and A here, is 878, right? And for an American call, so it's a call, CA is American call, and the binomial, we're getting that difference in price. So the option must have exercised early, or it can be exercised early, yielding a higher value for the call, the American call compared to the European call, right? And in that instance, then you're exercising early. So the trinomial and the binomial are producing different results. But if the option doesn't exercise early, then you're getting the European value, and the trinomial and binomial, we can say they're equivalent. Okay, now to demonstrate a little bit more fully that relationship, I'm going to come down a little bit further here. So we've reviewed this before, how to build a tree, the American tree. We've reviewed this idea, okay, what's the basic maths in terms of the relationship between the trinomial and the binomial. So this, we've explored this idea. When we square the binomial u, we get the trinomial u. And when we square the risk neutral probability of PU, when we square that from the binomial, we get the trinomial PU, right? Okay, so we can explore a little bit then the European. One of the things I've done here is I've come down and set up in Excel the European trinomial and compared directly to the European binomial tree. And I've done this in Excel. And so basically the set of numbers that we have here are the same as before, right? And I set up the same binomial tree in Excel. And what we observe here is every second step. So again, following the idea coming from Rubinstein, that is, one could hope that the trinomial tree could be parameters so that it could be interpreted more fundamentally as a binomial tree in which every other period were simply skipped, right? And to demonstrate that, I've set up the binomial tree, stock price tree, and then the pricing for the European tree. Again, we have that here, right? The European trinomial European, so the results I've obtained. And then I've set up done the same, right? But for the binomial, right? In the Colab, right? And I've created the stock price tree. And if you notice in this, so this is the stock price. Now it again, for the binomial, this is the up, this is the down, this is the up and then down, this is up, up. But every second set of nodes, right? If you skip a set of nodes in the European and in the American tree, the stock price tree, you can observe that the values are the same. So I start off at 100 in the trinomial, and then step 1 in the 9-step tree, I have these 3 nodes going up, going across, going down. But for the binomial tree, I would have obtained the same, going up, up, going up, down, going down, down. So I have 84.93, which is the same as here. And again, if I go up, up again, I get 13862, 13862, 1174. So embedded in that elegant world that Mark Rubenstein describes, the trinomial model is a special case of this binomial. Right? The trinomial model is a special case of the binomial. And when we do the backward recursion on the binomial tree, comparing against the trinomial, we also obtain the same results. If you observe 721, 39, 721. Now, if you want to run that experiment, observe that I'll show you how to do it in the derivative markets package available in R, right? And so if we run this double R, I can load in this package. It's a package created by Professor Robert MacDonald, who published Derivatives Markets, which is now in its third edition. So to accompany the book, he has Derivative Markets. We could find that package, find an R package. We can look here, deriv markets. It should be here, deriv, this one here. And the author is Robert MacDonald. And then there's some code and there's functions available, and it's quite extensive, right? So it really is a beautiful package, and you can run these codes here also. So if you get a function, for instance, source code, and let's say a compound function like R, you could take that snippet of code and then run down below, right? So it's a very nice function. So for instance, I've loaded this package into R, the derivative markets. I've come down. I'm exploring these relationships here, right? 878. Let's take that down a notch. And then I could create, if I want that output, let's say we want to run a binomial model with the same stock price, exercise, risk-free rate, volatility, risk-free rate, maturity, dividend, 18 steps for the binomial. If I run that, call it X, create an object called X, then I can output that out here, right? So basically, I can get the stock price tree. I can get the values like the P, the U, the D, the delta T, and then I can take a look at the stock price, the option price tree, and the stock price tree, right? And if you like, we can then go on and save that data. So for instance, if I wanted to write this out as a CSV file, so if I wanted to save the stock price tree and the European tree, so the option tree and the parameters, we could run the snippet of code, and those files then would load in here. And then if I could download those files, so if I just wanted to look at the European tree, so let's just see what's there, the stock price tree. Let's download. And we can open. And the values I obtain are for the stock price, the European stock price. Right, so that's a very nice feature. Now, these values that I have here are the same values that I have in the Colab that we were just working with. Right, so so the values that I have here, I obtain those from they're the same as what I have here, right, from this output. And then the stock price, the option price tree, these values are the ones that are here. So if I double click on that, they'll open up. Actually, the next one, the option price tree, right? So we can go further all along and explore that. Now we need maybe to show more. You need to download it and then you can observe. But that's 721, 1049, 740. are the same as what I have here, 721, 1049, 470. Right? Okay, so that creates then these packages that are available in R. You can run them in the Google Colab and you can explore quite a bit. I've put in, if you want to check out, you can run these scripts, R scripts, once you've installed in the derived markets package, and you can output the different option price trees, stock price tree, and so on for the binomial. Not for the trinomial now, and then you can save into your content folder, which is available here, and you can then download if you want to. If you close down this Colab, when you open up, these are gone, but you can download while the project is live. You can download to your computer, save them, and use them again. I did the same for the American tree, right? The binomial tree, and again I can save those in also. So if I run this command and save, if I refresh the content folder, we now have the American tree as well. And we can plot using the derived markets package. We can plot the stock price tree and observe the early exercise. So this is the 9-step tree. And the value for the American option is 898. We observed that before, but if I change this to European, say false, right, we can explore that tree as well, right? So there's no early exercise except at the end, right? So let's change back to American true and note that the value, the option 721. So that for the 9-step tree, we're getting that 721. We're going to change this back to true to get the American value. So then that's 898, right? Which is consistent with what we had before. Now I've also set in the F options package. The F options package is, Robert, is from Detail Verts, which I've left a link to above. And then you can run snippets of code. Maybe we can explore that. If I go back to F options, find F options. It's another package in R, F options. And it's F options. Let's explore a little bit. F, try that again. I'm F options. Should be here. F options, R metrics, right? And we can look at functions, and we have here source code, right? Now, anything that we have, we can load in. So this is different option valuations. And if we come down to the end, we can load in our code here. So for instance, we have a snippet of code where I generate this tree, right? Can do the same here. So Cox-Ross-Rubinstein tree, the values are 100, 100, 18-step tree. So the same parameter values as before. And we can run that live so long as we have library F options open. If I paste that in and run, it should generate the this tree here, right? Okay, so I'll go back to the trinomial model and run this snippet of code, right? Now it's difficult to follow, but this is for the American option. And if I change from CA to CA to CE, so this is the again the same. This function is the same as the function we've loaded into Google Colab, but this is from the package, and it's providing us with graphing capability. And I do the American option, we get this value. It's difficult to see. This is the European option, so 721, barely legible. I can make that more legible if I adjust the dx or the dy. So in this case, I adjusted the dy, And you can see here we have, and I changed the limits from 5 to 10. So we're getting the 0 region, but you can observe here that 721 is consistent with the value we have here in our option price tree, the 721 that we had observed before. Wrong spreadsheet. So the spreadsheet here, the 721 that we had here before, right? Okay, so let's go back into Colab for a brief moment. The tree that we've run here is 721, 10, 5, 475. When we compare against the trinomial model, you can see it's the same, right? So we've created this, we've explored a little bit, if you like, the circumstances under which the binomial and trinomial model are equivalent, right? Okay, so I'm going to leave this Colab beneath the video clip. You will be able to explore it, and I'll also leave a link to the VinegarHill website. It's there in the Colab as well, where you'll be able to explore a little bit in sequentially how you'd set this up. So if you're new to trinomial models, you don't understand the C++ code and so on, I've left these more introductory video clips that are there that will be available that would guide you through that process. And the motivation for this video clip is really to look at under what circumstances the binomial and trinomial models are equivalent. Okay, let's leave it there.